Okay, cool. So yeah, welcome to I guess in persons or section 10. So this week we're going to be talking about all types of things related to parallelism. So I had to cut a couple of things out for like in terms of being in person or like live section today, but I'm going to try and go back and talk about them like afterwards and recorded so that way you guys can get a better sense of them. But based on the poll and like the attendance kind of thing, it was just like everything is kind of shaky, which makes sense because like it's, I think you guys just talked about like cache coherency and like this past Monday and then parallelism last week, right? If I'm getting it correct. Okay. That's okay. That's also okay. Okay, so yeah, we'll get started. So the general breakdown today, or the goal is going to be, so we're going to go over some parallelism basics, and then kind of what it is. And then we're going to talk a little about DLP, which is data level parallelism, and then TLP, thread level parallelism. The last one, instruction level, is interesting. Sometimes it's in scope for exams, sometimes it's not, but like you don't have to know too much about it, just kind of generally what it is. I'll touch on about a little bit about it verbally, but I'll include the slides and what I send out later. And then the last one is going to be cache coherency. I think the cache coherency one is typically a pretty hairy subject just in general. So we'll see how much time we can devote to that, and I'll stay a little bit longer. And also, as always, let me know if you have any questions whenever. So let me open the chat so that I can see that. Okay, cool. Yeah, kind of getting started. Do either of you guys have any topic that you want to, or particularly want to spend a little more time on, or just kind of go through everything? Go through everything? Okay, cool. Hello. Oh, there we go. Okay, so parallelism in general. Well, what is it actually? Okay, so well, parallelism is the idea of performing any kind of operations at the same time. So whether that be simultaneously or duplicated or anything else, so it performs things basically at the same time. And so this may address like maybe the same instruction. So we're performing the same add on like different pieces of data, the same data. It might be different instructions, might be the same data, might be different data. And so this is what kind of encompasses some combination that will define basically the different types of quote unquote parallelism that we'll see later. So parallelism overall, in order to actually work, it has to be firstly supported by the software. So what you're writing has to incorporate it in some way. You can't just have code and magically expect it to like say, oh, I'm going to like do these two things at the same time. So you have to make sure you're actively doing that. And the hardware itself also has to support that. So we'll talk about this a little bit later. But if the hardware, say, doesn't actually support something, even if you have, say, everything else right, it won't actually be able to do it, perform the operations, mostly because like you just don't have the capability. So like imagine if you have like RISC-V kind of operations, you're like, you know what, I'm going to do 64-bit floating point operations. If you don't have the 64-bit registers, the right things aren't going to happen. And then the last part is the actual compiler itself. So a lot of this class so far has been like about the compiler. So like, oh, if this just isn't supported, then you can't get this result. And so parallelism is kind of the same thing. So in project 4 and in the more recent labs, you might notice like things like SIMD or thread multi-threading. And this is all things that are supported by GCC. And so the GNU C compiler. And so that's why you're able to get the optimizations as a result. But if it's some kind of lamer compiler that doesn't actually support that, even if you have the two other things, it won't actually work. So why do we need it? Okay. So inline operations usually are easy to understand, and it's like easy for us to process. We see an instruction, we see this piece of data, we know what's going to happen. So it's easy for our human brains to understand, but things are inefficient. So if we recall like maybe like a month ago or so with the data path and pipelining example, well, data path, like if you have these individual sections that are kind of operating one at a time, sure, it's easy to understand, it's easy to kind of logic out in hardware, but it's really inefficient because a bunch of things are asleep. So the same idea kind of exists for basically the rest of the system as well. So if we have the hardware support, why not? And so this takes advantage of two things. The first one being we often have similar kind of operations or the same operations being applied on large pieces of data in sequence. So like, for example, if we're going through a loop, we're doing the same thing pretty much on the data, even if it's conditionally, but we're performing the same operation. So why not do that all at the same time? And the second idea is that most operations don't require 100% of CPU support. So what this means is basically a single add operation won't require your computer to be only focused on that, whatever your computer might be, focused on that one operation or one support at the same time. So technically speaking, some of the CPU can be allocated to performing other operations. So parallel processing overall allows us to take advantage of whatever units might be sleeping, and so the system itself can kind of schedule these things. Are there any questions so far? Okay, cool. Let me also, I just realized I don't have a copy of slides open in front of me, so I have to keep turning around. It's a little bit awkward. Oh, just disconnected, but hopefully it's not this. Okay. So then, we already talked about this a little, but if it's starting to sound like pipelining, that's because it's exactly the same idea. We're kind of just doing things in parallel. Yeah, so far, are there any questions? Okay, cool beans. Then kind of moving on to the next part. Okay. So this, the idea of Flynn's taxonomy, if you've maybe like listened to lecture, this might have come up, but unfortunately I couldn't figure out how to get the transitions to work on here, so you're going to get all the information at once. But the idea of it is basically it's a grid kind of form, and you have two options for the two things that go into instruct, or that go into basically a program, so that affect its output. So the first thing being whatever data that you have that needs to be processed, and the second one being what instructions that are actually, or operations that actually operate on the data itself. So if we start on the top left-hand corner, we have one single instruction that's operating on one piece of data at a time. So this might be like, this might be an array, or it might be like a single character. But when we say one piece of data, it just means that we're not looking at things kind of consecutively, or several different things. So in most simple CPUs, which don't exist nowadays, but did very early on, this is what we had to think about. We had one operation performing something on, say, one register or one, say, bytes worth of stuff. And it's really, really easy to think about, but it's not really scalable because we need to do more than one thing. And so oftentimes we'll say, okay, well, what if we need to have like multiple pieces of data as input? That kind of brings us to the top right-hand side, which is SIMD. And so this is basically taking advantage of what we saw earlier, saying that, oh, one operation might have to be applied to like, I don't know, 50 of these like pieces of data, all kind of in consecutive order. So we're going to try to do as many as we can at once to reduce the number of times that operations have to be called, because we know like every function call, every additional instruction is extra time. And so this is the class of vectorized instruction. We'll talk about this in a couple of slides, but just the same instruction, same operation kind of being applied on different vectors. So these are usually consecutive, or the data is usually consecutive. And an example of this will be the Intel Intrinsics. So we can take a look at that later if we have time. But that's the main thing that we're going to be using in terms of SIMD support in 61C. If you're curious about it, there's a lot of other different types of SIMD support, but this is just the one of the common ones. And then kind of going to the bottom left-hand corner. So now we have, instead of multiple pieces of data, we're going to have one piece of data that's going to have several instructions operating on it at once. So this isn't the same thing as saying the same instruction being applied at the same time, but rather like several different instructions being applied at the same time on the same piece of data. Practically, this doesn't really exist. Any ideas why that might be? Say like several instructions doing one piece of data.
But then, you know, the order is like mixed up.
Yeah. So like usually if we have instructions operating on one piece of data, we want it in a specific order in some way. And if it happens all at the same time, that probably isn't going to happen. So either you need to have a way to fix the order or like figure it out in that sense. So that's why that's typically not supported, Ms. C. And then the last category is if we have multiple different instructions on multiple different pieces of data. So this is what's kind of falls under the cloud computing kind of aspect. It's a little bit hard to think of like in terms of practically how that would even work, but that would be like on the scale of like warehouse scale computing, a lot of stuff happening at once. You don't have to worry too much about it, but basically you can just think of there's a lot of concurrency going on and a lot of logic. Are there any questions? Okay. So we're going to take this and kind of apply it to see what it might look like visually. So we're gonna have two. So we're gonna have 4 different diagrams. So we're gonna identify which one's which. So we have 4 different options: SysD, SIMD, MISD, and MIMD. So if we start on the left-hand side, which one would this represent? So kind of taking a look at this, data pool and instruction pool is all the operations and all the data we're gonna operate on, and the processing unit is just kind of what carries it out. So on the left-hand one, what does it look like that might be?
Looks like one instruction, one data.
Yes, and we just disconnected.
Like, you haven't labeled, but
Yeah, it's SysD, so single instruction, single data. Yeah, exactly. So this one's going to be SysD, and it's because, like, you can see, one kind of data bus is bringing it to one processing unit, which takes care of one instruction. And something that we can notice between the two is, as soon as we have like multiple different things going on, we'll need multiple processing units or multiple cores of some sort. So that's one of the key aspects. So that's SysD. Then this one, the one on the right, which one would it be?
there's multiple instructions, multiple data.
Yes, so that is a common mistake. So multiple data, multiple instruction has to be like different ones. So if we look at this one, the data pool, we can see there's only one bus that's being copied to all 3.
Got it.
Yeah. So this one we have multiple instructions. So the one on the right would actually be SIMD, because we can see that just different instructions are operating. Wait. No, it's the other way around. Oh my goodness, I labeled it incorrectly. I'm sorry. This should be MISD, because it's multiple different instructions. I flipped the 2 by accident, but yes, this should be MISD because we have multiple different instructions operating on the same piece of data.
So like, if you wanted to draw it for it to be like MIMD, would the arrows be like in different areas of the spectrum?
Ooh, yeah. Yeah, no, exactly. But yeah, what you're saying is exactly right. So we can see for MIMD, like the one on the right. But this one, the one on the left should be SIMD. I flipped the 2 by accident. But we can see for MIMD in particular, we can see that each, like the processing unit doesn't suddenly like explode in terms of quantities, but we can see that for each one of them, they're going to have like different combinations of instruction and data. And so they're, yeah, this one like looks a bit funky, but I couldn't get the number of arrows to work out correctly. So diagram wise, it's just meant to say, oh, these each have like things that are being copied to each of the processing units separately. So, and then the one on the left should be SIMD because we have different data that's being taken from a single instruction pool.
What's the one on the right?
So the one on the right should be MIMD. This one, I know it looks, I think it looks a little bit funky. I think actually what it should look like is, instead of having like these arrows, it should just be directly pointing into them for separate ones. But yeah. Okay, so now that we have that, the idea of actual speed up, so what does this mean for speed up itself? And because transitions, we see we have a singular side equation here. So this means that we are actually, we know that things aren't always going to be perfect. So remember from like the pipelining thing, even if we have 5-stage kind of pipelines, we don't ever really have 5 times the speed up. And the reason is because there's overhead on a lot of different aspects. And we'll talk a little bit about that later. There's different types of overhead and things that we have to worry about for each type of parallelism. But generally speaking, parallelism has limits. So if we speed up part of a program, the speed up of the whole program is bounded by the size of that individual part. So this is speaking in particular to SIMD and multi-threading usually in terms of speed up. But basically what it's saying, say if we have a program that's 50% of it is able to be parallelized in some way, 50% of it isn't, we're not going to, and then say like the parallelized part is going to be like 5 times the regular speed. The whole program isn't suddenly going to be like sped up by 5 times. It's only the part that's theoretically under the speed up plus sped up part that's going to be multiplied by 5 times in theory. But we still know that there's going to be costs and benefits to each of these. So this is still going to be the optimized version of it. So if we take a look at what that actually means, so the S is representing the length or the percentage or like the decimal version of the non-sped up portion. And then the P is the speed up of the remaining portion. So the 1 minus s portion. So the p is the part that's actually sped up. So we can see, like, in terms of the actual equation there, we can say, oh, well, the speed up part is sped up by a certain amount, so p. And then so from there, then we can add it to the non-sped up part in terms of how much there is, and then we can figure out how much it can actually be sped up by. Does that make sense? So, okay, we can go through an example really quickly. Let me actually maybe, can I draw it on here? No, I'll just exit presenter mode for a second. Okay. So, am I on the right screen? Yes, okay. So if we take a look at this, for example, if we have a program that's 50%, 0.5 is able to be sped up by 4 times, and 0.5 isn't. And then so we can say, okay, well, we know that the 0.5 part, so like originally 0.5 of the time is going to be taken up by the non-sped up, 0.5 is going to be taken up by the other part. So the speed up portion is now going to be, 0.5 divided by however much we can actually speed things up by. So that would be 0.5 divided by 4. So that gives us, I'll make it 2 to make it easy on my brain. Actually, this is 0.125. Okay, I'm just slow. This is 0.125. And then the other part of it still remains the same because it's still going to take that quote unquote 50% of the time. But now the other part is going to take up less time. So our total amount of time is going to be 0.5 plus 0.125. And so now we can get like, if we divide the two, that's going to be 0.625. So then if we do 1 divided by 0.625, this is going to give us how much speed up from the original, because like originally we're going to have a time of 1, but now we have some amount that's a 0.625 of whatever time it would have taken us originally. So taking the reciprocal of this, it gives us the amount of speed up. Does that make sense? Yes. So, so it's like, yeah, it's like saying taking
the total program.
Yeah.
Okay.
Madeline, does that make sense? Okay, cool. Yeah, so overall, this just means that this is in theory the maximum that we could ever speed up by. And we know that this is not something that we're going to hit because we don't have actually the like perfect amount of that with no overhead at all. So this is only in theory. So kind of going into the first part of the actual speed up itself then. Oh, wait, this is the wrong. Okay. So going into the DLP portion, so this is data level parallelism. This is going to be the whole like SIMD aspect of things because we're going to be acting on the same multiple pieces of data with the same instruction. So this kind of introduces generally the idea of vectors and vectorization. And so overall, vectors in kind of computer architectures just mean that you have different pieces of data that are placed side by side in a big register. So if you want to think about it in E sense or an algebra sense or linear algebra sense, it's exactly the same thing. It's just hardware has to support it. And so whatever operations actually exist, they have to be applied to all the elements. So you can't selectively say, I want to apply it to 1 and 2, but not 3 and 4. So any operation that you have to do has to be applied to everything. So which also means if your array says, I'm going to for the first 2, based on like the element count or something, I want to apply it to these 2, but not these 2, then you're going to have to figure out an alternative way to do it. And there are ways to do those kinds of things. It's just trickier because you have to go a longer loophole. So conditional, kind of speaking of that, conditional operations are possible. You might think about this in project 4, but it's definitely not necessary. But the idea of it is basically just using masks by generating kind of say, if I want like these elements to be quote unquote turned on, these elements to be quote unquote turned off, you can use Boolean kind of bitwise algebra or manipulation to be able to turn off and on certain elements in a vector. I can talk about that more later, but yeah, it's possible. This is totally just me being biased, but 152 is super cool. They do such cool things with RISC-V vectors. I won't talk about that now. But yeah, this requires the systems to have the hardware support, such as properly sized registers and the compiled support. In the interest of time, I'm going to speed past all of this because, yeah. So reading Intel intrinsics themselves, so it can be really confusing when looking at the guide itself. So if you want to take a look at, I will drag it over here. This is what Intel intrinsics look like. If we take a look at, hello, there we go. So if we take a look at it, it's kind of like nuts, just kind of going from the get-go. But they have a really good guide in terms of how like things are actually read and how you should kind of read through them. And so the way that you kind of go through them is, get back to the slide. So they follow the following notation for the actual functions themselves, or the intrinsics. You have the double M part, and then you have the intrinsic operation name, and then you have the suffix. So the name just implies whatever operation it is, like comp or like intersect or add or whatever. There's a lot of different kinds, and usually gives you a short summary of like what kinds of things are done. And then the suffix part identifies the data type and how it's going to be handled inside register. So if you recall from data path stuff, if say you have a 4-byte register and you only have 1 byte's worth of data, you need to figure out how to fill up the rest of the bits with whatever data it is. So this just kind of identifies all that information. So kind of quickly going through them, first 2 letters indicate whether it's packed. So which basically means that whether or not it should be like, say, if I have 8 bytes worth of space and my elements are 2 bytes, should I be 2, 2, 2, 2 and fit 4 of them? Or for example, if it's extended path, it might be extended to say like 4 bytes first. So you're going to have just 2 bytes worth of like space that's being filled up by empty bits, or whether it's scalar. So scalar is not really used in this class, so you don't have to worry too much about it. And so this might look, for example, or actually the rest of it should come first, but the rest of it basically is indicating what kind of data it is. So S is for single precision, so 32 bits. Double precision floating point is a double 64 bits, and then signed 128 bit is I128 or I whatever number of bits that you want. And then unsigned just has a U at the front. So if it's signed like 64, then it's going to be I64. And so this comes out to instructions kind of looking like somewhere along the lines of, let's bring this back really quickly. So we take a look at this like EPI 64. So this means it's extended text, an integer of size 64. And because we're in the type MM256, this basically means that we have 256 bits worth of space in each of our registers. And this is going to mean that we're going to be extended to the 64 bits, which means that in 256 worth of space, we can fit 4 elements in there. Does that make sense? Kind of? Yes, okay. So it gets a little easier as you go along, but basically it's just usually things are in multiples of 4 when it comes to SIMD. And then so kind of going off of that, then you'll also notice that on the other side, like the return, there will be some kind of return type for the elements or for the arguments. And those will generally look like they have 2 underscores and M and whatever suffix kind of it matches. So this usually takes time. Usually you'll have instructions in front of you for an exam, and you'll hopefully have the guide when you're working on the project, so you don't have to memorize them. Are there any questions so far? Okay, and then going about SIMD, how do we actually do this? So the general pseudocode for SIMD operations involve kind of the following steps. So SIMD is usually used, say, when we come to doing loops worth of things, because those are like loops are the places that we know we have a set amount of stuff that we want to iterate through. And so we iterate over the data in groups of usually 4 elements. Sometimes there'll be 2 if you're, say, doing like, oh, I have 128 bits worth of space and we want to work with doubles. But you just want to take a look at like whatever the spec says to see how many elements it actually is, usually 4. And then so we load a contiguous group of 4 elements from whatever array usually that's providing the data into a SIMD register. And then so those will just usually use kind of load U or load load operations, and those exist across the intrinsics. And then whenever you're performing memory operations with from or to memory, so load or store, you always want to cast the array that you're working with to whatever type it is. So M suffix. And this just basically tells us that, oh, we're going to be working with vectors from now on. And then so you perform whatever operations that you typically would on the SIMD register. So typically this just involves like kind of manipulating like what you would do regularly and then kind of branching it out to think, okay, I want to perform on 4 at the same time. Can I just copy one-to-one the operations over? Sometimes it gets a little bit trickier with masks and things, but it doesn't usually deviate too far. And if necessary, you want to store the elements back with the same memory operation kind of rule that we see earlier. And the last part is the tail case. So this is the part that trips people up a lot. So if the array length itself isn't a multiple of 4, we want to make sure that we actually take care of the last 1 to 3 elements. Otherwise, we're just dropping it off the end of the array. So say we have a size 4 vector and we have an array length that's denoted as array like ARR len. So if we have something like this to say, oh, this is where I want to end before I check for the tail case, does this work? So will this get us to where we want to be? It's okay. You can just throw out an answer. I messed up the first time I thought about it as well. I could not wrap my head around it.
Like you want to, let's say it's like 13, right? And you want to divide it by 4, then you get 1. But that's not, I mean, I'm thinking of a it doesn't give you it gives you like a floating decimal point thing. Right?
Not exactly. That's not what I was going for, but yeah, it does give you a remainder. So say if we like, let's just make a new slide, and then. We don't need to do that. So in C, the operations, as long as they're marked as being ints, you don't have to worry about them. You don't have to worry about them kind of taking up too much, like, or they don't just get cast into floating point. So it'll actually truncate it. So, okay. Because I keep losing my mouse, we're just gonna do it like this. So say if we have array length is equal to 13. So we know that, let's say the array is just gonna have 2. Okay, so this has 13 elements. So we know that we're going to end at some point. So if we divide it by 4, it's going to truncate it and get us to right here. So it's going to take off, or let's say, okay. So 13 divided by 4 is going to be 3. So that's going to, and then so if we iterate through it in groups of 3, that's going to give us, let's see. So we're going to have one group of 4 right here. Yeah, because when we're working in like vectors, we have to take by groups. So we also have to increment by groups of however much. So it's going to give us up to right here. So yes, that looks good in theory, right? So let's like write a quick for loop and see what happens. So for we're gonna 0 I is less than array length divided by 4, I plus equals 4. Oh my goodness. So if we have something like this, how many iterations do we actually go through? So we know that array length divided by 4 is going to be 3, right? Wait, oh, oops, I just realized. Let me see. sorry, wait, give me 1 sec. Oops, okay, let's give us, wait, rats. No, I was trying to think about something. Oh, I think it was, okay, I think this was gonna be a plus plus, yeah, because otherwise we're gonna get it to be too high. So we do something like this. So we go through the first iteration, I is gonna be 0, we go through the first block, I is gonna, then we increment it by 1, I is gonna be less than 3, and then we get the second block, which is I is gonna be 1, third group, I is gonna be 2, and then we're gonna increment again, right? So let me see. Oh, wait, I realized, sorry, I'm sorry. I just realized what I was trying to do. Okay, so array length divided 4 doesn't actually, it's fine as long as we increment by 1, but it can get confusing because if we try to do memory operations like that, it involves a lot of math later on. What I was actually trying to get at was if we do just I is less than array length like this, what would happen? Yeah, because we're gonna go to this and say, okay, well, like whatever this is, it's not gonna actually like be passed. So then it's gonna try to take 12 and then 3 spaces after that. So we have 3 spaces worth of garbage. And then so that kind of messes with our data. So yeah, exactly. We don't want to do that. So instead, what happens is instead of doing array length like that, or even array len, which is incorrect as well. So not array len. So instead, what we want to do is we want to do array length divided by 4 multiplied by 4. And so this gives us kind of the perfect truncation that ends right here at this element, saying, okay, if we go past any further than this, then we're going to overshoot because this is our last like boundary of group of 4. So it has no risk of ever going over. So this gives us the ability to say, okay, I'm going to go through, iterate in groups of 4, but we're not going to overshoot. Does that make sense? Yes, okay. So yeah, that's the biggest reason of why that happens. Okay, that's generally for DLP. Usually this comes with practice as well. I wish I had time to go over more questions. If I have time tonight or tomorrow, I might go through and record a few of the questions from the worksheet. But yeah, I'm also going to briefly talk about TLP, and then we're going to go into actually cache coherence because that's usually a big part of what's confusing. So, so we talked a little bit about a speed up and why like things don't actually happen, but the idea of TLP or multi-threading is basically saying, okay, well, so far we have the idea of multi-processing, which just means we have multiple processes happening in one memory space. But something that we know about that from the virtual memory part is that all of these different processes, they have separate pieces of memory, separate locations. They're basically entirely, they are black box in their own kind of in their own black boxes, and they don't actually know about the existence of anything else. But TLP is kind of an opposite, not really opposite, but it's like a little bit, there's a bit of distinction from that. And so threads, what they are is you can think about them as like lightweight processes. And so what that means is it's going to do a lot of the things that processes do, aka like do things separately in parallel. It won't really actively mess with each other. But one of the biggest things that differentiates that from a separate process is the fact that it shares the same memory space. So what that means is there's the possibility for one thread to mess with what data the second thread might be accessing. So that is one of the biggest differences. The registers and other values such as like the stack and things are copied by itself into a different part of memory, but the memory being shared is the most important thing. So in theory, we should be able to speed up things to the number of threads that we have. So with one thread, we should be able to speed it up or have it sped up once, which is just its regular speed. With 2 threads, we should be able to do 4. With n, we should be able to do n. And this doesn't actually work. And the reason for that is because we're ignoring a bunch of overhead that exists in just spawning the threads themselves. So like I mentioned earlier, it has to copy all of the registers. It has to copy stacks. It has to go into operating system, say, hey, we want to perform this operation that's like you can only do. And so like those kind of separate entry points into operating system area and just doing all of this takes up time. We also increase overall program complexity, which means it has to handle other things to be able to parse it. So maybe more instructions. We also have possibly race conditions, which we'll talk about on the next slide, which is kind of what mentioned earlier in terms of memory being messed with from one thread to another. And we're also constrained by hardware specs. So usually we have several hundred threads kind of operating on, say, 4 or 8 cores on our laptop. And the reason that we can have so many threads on so few cores is because we don't need to have 100% of CPU for every operation. But if we kind of even go beyond that, say if we have 1,000 threads, then what ends up happening is like all the threads say, I want some CPU space. But then if it keeps on kind of changing between the different threads, you might remember kind of the idea of thrashing or like context switching. Kind of from operating system OS kind of thing. Context switching is basically saying process 1 has like all of this setup information, and then to execute process 2, it needs to kind of save that somewhere and then kind of load everything for process 2. And so the idea of thrashing is basically saying, if it keeps on like the system keeps asking you to change out this information without making any significant progress, then you're just wasting time without actually doing any calculations. So if you have too many threads, that can also happen if you don't have the proper support. And then you also have non-deterministic behavior. So this is basically saying threads don't execute in 0, 1, 2, 3, 4, etc. order. It might be, it's just some entire random order depending on how the system says, I want you to go now. So you can't expect it to have some kind of result. So race conditions. It exists because of the fact that threads can share the same memory space. And so this can cause an issue in several ways. So let me see. Okay. So threads overall can be swapped out at any time by the operating system. So the question then arises, what if one thread modifies memory that another thread then uses? If we have this code, so here, there we go. So we have a static counter, and we're going to assume that there are 2 threads, and then we're going to parallelize it with the pragma OMP parallel 4. And so that's pragma is just saying, oh, it's kind of just a regular intrinsic in C. OMP is telling us that this is kind of the library that we're trying to use. And then parallel is saying we want to parallelize this next chunk of code in between whatever next curly brackets we see. And then the 4 is telling us this is a for loop that we want to parallelize, instead of saying, I want to do the for loop entirely twice, which is what would happen if you don't have the 4. Does that make sense? So basically it's saying, okay, if we have pragma OMP parallel without the 4, it's saying in the next kind of section of brackets, so what you would have to have would be a bracket, or hello, there we go. You would need to have a curly bracket here and then a curly bracket at the end, just saying kind of this code in the middle. I want you to copy this code across all the threads that I have and then execute them all at the same time. Whereas if we say this parallel 4, it's saying, I recognize that the next kind of section is a loop, and I want to divide up the work instead of copying it like 5,000 times. So we're dividing this work from going from 0 to 0. I is equal to 0, I is equal to 1 between 2 loops. And so counter will increment, and counter starts at 0. So the question then becomes, what is counter at the end? So you see, like there can be a lot of different possibilities. Yeah, it becomes quite annoying. So I'm just going to go through this really quickly in the interest of time. But we can see that, okay, if we translate this to assembly code, which is what the system will be looking at. So we are going to load the counter into a register. We're going to or the label into a register, and then we're going to access whatever value is at that register. So in this case, T1 is going to contain 0, T0 is going to contain the address of wherever this counter is actually stored. And then so for the add-I part, that's going to give us an initial bump in terms of like the incrementing the counter, because it's going to be counter plus 1. and then we're going to save it back into wherever counter is. But the problem is this operating system can interleave the two threads. And what that just basically means is we see that we have 4 different instructions that can be executed for like inside the for loop. And then so what it's going to say is, well, both threads are going to be executing this. We don't know which one's going to do what at what time. So theoretically speaking, we could execute all of thread 0's instructions here and then execute all of thread 1's instructions, which is what we're expecting, and that's what we want. But it doesn't actually necessarily have to do that. So what we can see is, okay, well, thread 1 might be loading this into counter. I don't know if you can kind of see, but it's kind of greenish. It's going to be green and red. Thread 1 is going to load the value of counter, so that's going to be 0 at the moment. Now the system decides, I want to mess with you and say, let's load thread 2. So now thread 2 is going to read from counter. Or if thread 2 is going to locate where it is, and it's going to read from counter, so they both have 0 at the moment. And so now it's going to say, okay, thread 2, we're going to add, we're going to bump you up by 1, so counter technically increments, and then we're going to switch back to thread 1, say that increments again, so they're both at 1. Now this doesn't actually look right because we wanted them to increment on top of each other, but because there's no communication between the threads, they're each doing their own thing. That doesn't actually happen. So now once we save it back into the counter and then we save it back into the counter, we can see that, well, we expected the counter to be 2, not 1. So do you see kind of like what might happen? So this is kind of what the idea of race conditions is, basically operating a system doing operating system things. So how can we actually solve that? Well, a couple of things. So this is just going to be thrown at you all at once for a second, but there are different ways that you can handle this. So that in OMP, so what you're going to be using for multi-threading, variables that are created outside of the parallel block. So for example, right here, we can see the pragma OMP parallel 4. Anything created outside of that is technically considered to be in shared memory space. So these are all shared across threads. So if you want to modify the same shared variable, you need to be either, like it says, really lucky, or you need to make sure it's locked in a critical section. This is critical sections basically mean only one thread can modify it at a time, and only when is it done, like saving it, say, back into the where the variable is living in memory, then another thread can kind of change it. So that prevents it kind of from going back and forth. And so there's other ways that you can do it. For example, like you can technically change the, instead of having like a public one, you can make it private and then kind of like glue them together at the end and stuff like that. But usually kind of starting out, you just want to put it in a critical section. It's saying one thread goes in until it exits, no other thread's allowed to go in. So this is another version of why, like say, multi-threading might end up being slower than expected, because it's like we want to make sure that correctness is there, if not the speed. So this guarantees correctness, but it might slow things down. Are there any questions so far? Okay, so going on, I think the next section was going to be ILP, but we don't really have time for that, and it's also not super important, so I'll just talk about in the second recording. The next part is cache coherence. So just as a quick like kind of show, are you guys familiar with the idea of caches and what they do generally? Just like, okay, cool. So cache coherence, basically what it does is it saves the caches from being destroyed by all of this multiple parallelism things. So the short answer of why it exists is because threads exist and threads make our lives difficult, even though it sometimes is nice. So the longer answer is this is the easier of two problems to tackle when it comes to multi-threading programs. So the kind of first like initial thing that we have is the actual problem itself. So we need a way for multiple threads to access the same cached data simultaneously. If you're feeling a little confused as to what this means and why we can't do this already, demonstrate in kind of like a quote unquote animation in a second. But the thing is, caches by default don't support multi-threaded reads and writes. AKA, this means that usually caches for each thread, there will be a separate cache, which also means, like, for example, we know that there might be like 4 or 8 cores. For each of the cores, there's going to be a cache. So you can't just like spawn another cache on the spot. And the thing is, having multiple caches will create multiple problems because caches are supposed to kind of align with what exists in memory. They shouldn't have inconsistency across it. But we have an instance say, what happens when one thread reads from memory and then another thread reads from it? Well, this is okay. Nothing's being changed. It should have the same data. But the problem arises what happens when one thread writes to a certain memory address, and then another thread tries to read from that, or say something has read from it before and then another thread writes to it, then we're not going to actually have the updated values. And so this kind of issue is kind of demonstrated here. We're going to go through this in a second. So it looks really kind of confusing and a little bit terrifying from the get-go, but basically what this is saying is, okay, so on the very top, we have kind of processes that are kind of going. So we have one process here, so 0, process 1, all the way up until process n. And so we're going to say each of these aligns with how many cores we have. So how many processing units we actually have to perform stuff. This isn't necessarily going to align with how many threads we have, because threads can be switched out by the system, but this is the hardware that we have for support. And then we have the different caches that correspond to that. So cache 0, cache 1, all the way to cache n. This looks like German. And we also see that there are different connections between this. So we have the processor 0, processor 1. It connects and communicates with the cache 0, cache 1 respectively, all the way to cache n. But we can see that the different processors and the different caches don't directly communicate with each other. They all connect to this interconnection network thing, which I'll talk about, like, say, in many slides, probably in 5 minutes or so. But like, we don't really know what this does right now. We don't really have any protocols. It's just kind of exists. So think of it as just a wire in a sense. And then we can see that this is just another layer that connects us to main memory and then input output. So this is already stuff that I have covered. You don't have to worry too much about it. It's just a way for basically buses to go back and forth. So some cache specifications. Just as a quick review, there are like 4 specific cache specifications, aside from like kind of like the size, the kind of writing policies and stuff like that. But for this particular, all of these caches are going to have 2 things. So it's going to have write back protocol and write allocate. So what that means is write back says, okay, when I've edited something, so the data in the cache is dirty, which means that it's not the same as what's in main memory and is newer, then we only want to write it back to main memory when we've evicted it for whatever reason. So up until this point, eviction only happens when another block kicks it out. So we're going to say when another block kicks our blocks out here, that's when things get written back to main memory. And then write allocate says, okay, when I'm fetching data from main memory, I'm going to fetch whatever is in main memory itself, put it in the cache, and if I need to write, then I'm going to write. So it's not going to all just say go and write, or sorry, bypass everything, bypass the cache itself. So their cache review, the other 2, write through is the opposite to write back. It's going to just bypass the cache and write directly to main memory. Slower but easier in terms of logic. And then write around is just going to say, okay, on a write miss, instead of say loading the the data line to the cache and then updating it there, we're just going to write it to main memory again. So again, these 2 are just easier to implement, but it takes more time and kind of ignores the cache altogether. Any questions so far? Okay, yeah, I know it's a lot, definitely. There will be annotations later below, so hopefully that helps a little. So, okay, now we can see that we've color coded things. It's a little bit light, but hopefully it's still readable. So we're going to go through and perform something. So the first operation that's going to happen is the system is going to run thread 0, so T0. T0 is going to just correspond to processor 0, process 0. So we're just going to say that. So what happens after we run thread 0? Well, oops, hello. Okay, after T0 runs, then we know that processor 0 is going to be active. So yes, there we go. Processor 0 is going to be active. So the next thing that we're going to do is processor 0 decides I want to read from memory address, or MA as we'll call it later, A. So what happens after that? We can see that we go through the cache, say, okay, it's not in the cache, then we're going to go into main memory because everything started out cold. And so once we have that, then everything kind of goes back and says, okay, now we're going to put stuff into the cache. So the cache 0 at line 0, not going to necessarily read that position, but we're going to just say that. Now it's actually warmed up because we actually have that. And so now it contains data A as well as whatever data in the rest of the data line there is. So we're going to say it has, it's been updated right there. Okay, cool. Now the system switches to T1 or thread 1. So now that's going to actually activate processor 1. So now processor 1 is going to be active. Processor 1 now wants to write to memory address A. So right now we know that process 1 doesn't actually have anything in the cache. It can't actually take a look at cache 0 and say, you have it right there. So instead, it's going to go to main memory as well, inspect it, and then bring it back to the cache. And so now cache 1 at line 0 is warmed up with the old data because it hasn't been written back to memory yet. And so whatever bytes that we're trying to write at position A are going to be written to cache 1 because we have a write allocate. So the star is indicating that the data has been changed. So we can see here that cache 1 has updated data, cache 0 has non-updated data because there's no communication between the two. Now the system switches back to T0. Processor 0 is active again. Processor 0 reads from MA0 for whatever reason because it decides it wants to do that again. And so we can see because it's in the cache itself, we know that it's just going to read directly from the cache. But what data do we actually read? Yes, exactly. So we expect it to read updated data A0 or A star, and because process 1 should have updated it, but any other process should be able to have that data because we don't want to have inconsistencies between the two. But instead, what actually happens is we're going to read A exactly like he said. And the reason for this is because the write back, write, allocate cache policies, first of all, means two things. So the write back, it'll only show up upon eviction. So in this case, it only gets evicted when the cache is, that line is kind of reused again. So that's very variable depending on what other stuff we called. And so it won't actually update the other caches at all. So that's an issue. And the write allocate, and on a cache miss, the data line updated or not will be pulled from main memory. So this is entirely an issue that can be resolved by having a protocol. So we love having protocols in CS things. So there's a lot more slides that I've hidden that show like different situations. I'll annotate those and let you guys look at them later. But overall, what happens here, oops, there we go, is the protocols kind of just ensure that on any kind of cache miss or cache write, that the other processors must be informed via the interconnection network. So this is basically saying the thing that you have there is going to be a communication device that tells us when certain things are updated, when we should evict, and when we should update permission. So remember, we have permission bits in caches, right? So up until this point, all the permission bits were saying, is it kind of okay to read or is it not okay to read? And so the protocols that we have that we're going to talk about in a second basically say, okay, there's going to be different states that it can have. I think that clock is dead. I've been looking at that and then I realized I was like, wait, no, that looks wrong. Yeah, I'll try to go through this kind of quicker, but so MI is the first one. So this is basically saying we have modified and invalid. So this is saying, has it been updated or is it invalid? And this is just overall not useful just because it means that it's either going to be in a modified state, which means everything else is invalid, or it's going to be invalid, which means we can't read it from the cache. So basically the cache is useless. So instead there's also another one that's called modified, shared, and invalid. And I'll talk about this in a second. Fancier one is messy, which is adds the exclusive permission. And then the one that's actually most commonly used and the one that shows up on exams in 61C is MOSI. And so this adds the owner kind of permission. I'll talk about this in the next 3 slides. So you don't have to memorize this. It looks terrifying. Don't worry about it too much. But basically what this is saying is, okay, we have our modified permission. And so what modified is saying is it refers to the state of a cache line when it's been written to. And so this can only exist in the cache of the processor doing the writing. So what this means is the way in which cache lines are observed is going to depend on what processor is looking at it. So say if we kind of go back to what we had before, say right here, we know that there's a cache, let's just say cache line A here, or a cache line 0. So in the eyes of kind of processor 1, cache line 0 has been modified. But in that case, then we could say, okay, well, processor 0, in the eyes of processor 0, out of the two that we've discussed so far, so modified and invalid, how should processor 0 view cache line 0 from its own viewpoint?
Modified,
Mhm.
so it must be invalid because class 1 modified it, or
Exactly.
but it only knows that through the interconnection.
Yeah.
Okay.
So the way that kind of it works, like generally speaking, is basically saying, okay, if I have something that's been modified, like say processor 1 has something that's been modified, it means that from its own viewpoint, like it has changed it, but nothing else can view a line as modified if something else has written to it, because you're kind of saying, have I done this to it? And so kind of if we go back, okay, cool. So if we go back to this one, the other one that we were talking about is invalid. And so this indicates the line must be reloaded from main memory upon next access. So basically what it means, it's saying something happened to the line in maybe one of the other caches or in main memory that rendered my cache's line invalid. So it doesn't mean that all of a sudden it's like it went kaboom or anything. It just means that, say, I don't have some updated version. There's something happened to this cache line and I need to get an updated version. So what happens then is through the interconnect network, it either goes directly to main memory and says, hi, I want that memory, I want like the new data, or it reads it from kind of the interconnect network. Logic you don't have to worry about. Basically, there's signals that get sent like back and forth between caches and processes. And it says, update this, don't update this, kind of a thing. And so this in the MI kind of setup, basically this means every other cache line in the one that hasn't been written to will be invalid all of the time. And so you can kind of see that like this basically means that the cache is just useless, because it means you have to fetch it from main memory every single time, as long as something else writes to things, right? Because otherwise, like if you haven't modified something, then by default it's going to be invalid, which means you have to go to main memory. So thus the cache doesn't exist, basically. Does that make sense?
Prop 1 has to write it or change main memory before prop 0.
Exactly, yeah.
But how does it know what to do that?
So based off of that, then so it's kind of like the packets that are sent like along the network. It's saying, hi, like in say the MI kind of setup, what it's saying is, if I've modified something, it's gonna tell you, oh, I also have to write it back to main memory at some point. Yeah.
At some point.
Yeah, at some point.
Okay.
Before the next access. And so this is all stuff that like if you're curious about, 152 does a whole section on. Yeah. But basically the biggest thing to take away from MI is saying modified means you've modified it. Otherwise you're invalid, which means you have to go to main memory. Therefore cache is useless. So that's why MI just straight up doesn't exist really. It's only used as kind of a demo. And then so the simplest kind of cache coherency setup you can have is MSI. And so MSI basically says, okay, the cache line in all other processors for which a write has occurred in a processor that is not itself is going to be invalid. So with this basically, it's a little bit complicated. So I'm going to actually go to this next bullet point before I go back to this. So the last kind of state that we have added to this MI-MSI protocol is the idea of a shared one. So what this is saying is, okay, this cache line exists in somewhere outside of just one. So it's going to be in 2+ caches. And so what this actually does is it says, okay, well, if it's shared by something else, then it can be in the shared state and it can be accessed, and it'll only be rendered invalid if some other process writes to that same cache line. So it's basically giving us a space that we can sit in that's not invalid, if that makes sense. Yeah. So overall, you don't have to worry about this diagram. It's just kind of what it looks like. This was pulled from 152, hence why it looks so crazy. But you can kind of just basically think of different actions that like different processes take will change where the cache lines will sit in its own viewpoint. Okay, I think, yeah. So, okay, the next option that we have is messy and mosey. So this is something that you might see from Dan Garcia's slides. I don't actually remember if they have it in this semester slides. I can go back and look and see what they have. But this is actually a really, really useful that I found quite nice. So what this is basically saying is, well, okay, all other states from the previous slide still hold. We're going to just add 2 particular slides, or it's not slides, states. So the first one is going to be an exclusive state. This is kind of the opposite of shared, and it says, I am the only cache that holds this cache line. And I know that because it's been like the cache line has already been marked as so. And so this means, say, back like in our kind of thread 0, thread 1 whole situation, the very first access that occurred, so the read from process 0, it's going to be in the exclusive state because it's the only cache for which it has stuff. And then this last one is the owned state. So by definition, this is the one cache that has exclusive official ownership of a cache line, and by default is always going to be dirty and can write to it, but the other caches can read from it. So from earlier, what we had was, we know there was a shared state, but that is by kind of understanding, it's not going to be modified. It's going to be, all the caches have only been reading from it, and as soon as we write to it, then it's going to be marked as invalid in all the other caches. The only kind of state is saying, hi, I actually like kind of exclusively have this. I'm the only cache that's going to be writing to it. Y'all can just come read from my local cache through the interconnect network, so you don't have to go to main memory every single time. So that's kind of the difference between all of that. If we kind of look at like this whole map thing, I think like if we start from somewhere, so let's say if we like start from, actually I keep wanting to go there, but say if we start from like just one process reading something, so it's going to enter and go from an exclusive state. So if we have the MOSI kind of set up, we're going to enter from exclusive because theoretically, if we're the first thing that accesses a line, it should be exclusive. And so if we as the process says, okay, I'm just going to keep reading from that line, cool, we're just going to get read hit, we're going to stay in the exclusive state. As soon as we get a write hit, which means like just the same process tries to write to it, it's going to jump to modified. It's not going to be an owned because no other process has tried to read from it just yet. So it's, and if we keep reading from it, if we keep writing to it, it's going to stay in modified. So far, does that make sense? Yes? Okay. Yeah, so even for read hits, it would stay here because we haven't written the previous change back to memory yet. So we see there's a couple of things that can happen here. So we see there's one arrow that goes out here. That's a probe write hit. This is a probe read hit. So what probe basically means is the action is coming from a separate process other than ourselves. So in this case, like say if we were a process 0 that was doing the reading and then now the writing to it, and then say process 1 decides to read from it. Now we know this particular thing is going to be still dirty, but we want it to be shared as well. So it's going to then go to the owned state. And so now it's going to say, I own it. I've been the one that's editing it. You can read from it, but like you're not going to be able to write from it just now. So we can say, okay, read hit, it's going to stay here, probe read hit. So we notice that like no other processes can write to it right now. It's just going to stay in this state. And now if we decide to write to it again, it's going to go back to the modified state because nothing's been written back yet. And then so on alternatively, we can see, okay, if we decide to have a probe write hit, then what's going to happen is say, okay, processor 0 has stuff that's been written. Another process 1 decides to write to it. Well, now 2 things need to happen. So like what you mentioned earlier, it needs to be first written back to memory, and then its own cache line needs to be invalidated because, well, now I don't have the most updated version. Main memory does, and whatever other process does, not me though. Yeah. So then we go to invalid, and invalid, we can see it does a lot of stuff. If we start from exclusive again, like, and then we say, okay, well, exclusive means we're the only one that has it. If some other process decides to read it, we are no longer exclusive. So now we're in the shared state. But so far, because we haven't edited it, we don't go to own. Does that make sense? Yeah. So basically, all of these arrows are saying, what do I do? What do other processes do? And then so it's viewing the cache line from our point of view. So if you think of yourself as a process and then all the other processes as like other people coming to do things and like looking at your cache line or looking at your cache, hopefully that helps. It's a lot to take in. Yeah. I'll go through like each one of the arrows step by step in the later recording that I'll do, but hopefully that helps. I actually have to get to a meeting. But let me end this real quick.